This our final video on vectors. We are going to work two past papers, 2017 and January 2016. So the first question starts off with a transformation geometry question, right? And that's a part of matrices as well. So question is to the matrix T C00D maps P onto the point Q. So this is a reflection, and if I'm not mistaken, this is a reflection if the point P is somewhere here and the Y value change, then this is a reflection in the x-axis, because this positive 3 became negative 3, and the matrix for reflection in the y-axis is mirror y-axis, that is 1 0. No, mirror x-axis, the reflection in the x-axis, sorry, and this is 1 0 0 minus 1. Now you can do the multiplication to see that. So C is 1, the matrix T is 1 0 0 minus 1, and if you multiply that, multiply P is 2 and 3 to get Q. 0 times 2, 1 times 2. Oh, we multiply matrices using row by column, if you see that in the earlier video. 1 times 2 plus 0 times 3, so this will become 2. 0 times 2 minus 1 times 3 is minus 3. So the C is equal to 1 and D is equal to minus 1. Next question. Determine the image of minus 5 and 4 under the transformation T. So we have to do a multiplication here. The transformation T is a reflection in the x-axis, not y-axis. 1 0 0 minus 1. You have to multiply this point here, minus 5 and 4, by that. I think it's best if you show the entire multiplication and just show the answers like here. So let's multiply. This is 1 times minus 5 plus row by column plus 0 times 4 and 0. 0 times minus 5 plus minus 1 times 4. So we have minus 5 at the top here. That will be plus 0, and this will be 0 minus 4. So the answer is minus 5 and minus 4. Okay, show that multiplication. Next thing, describe fully the transformation. Okay, the transformation T is a reflection in the y-x axis. That's the only description you can have. It's a reflection in the x-axis. So you write that out. Next, find a matrix that maps Q onto P. So this is the other way around. Okay, so let me show you. I'll draw a diagram to show you how we get that. And you're going to see, rather than just telling you what it is, I'll show you what it is. P was 1 2 1 2 3. P was 2 and 3, right? 2 and 3. Q was 1 2 3. This Q was 2 and minus 3. This was P, this was Q. If the matrix that mapped P onto Q was a reflection in the x-axis, then the matrix that will map Q back to P is the same reflection in the x-axis. So the matrix is still 1 0 0 minus 1. Okay, so the matrix that map Q onto P is the same matrix T, 1 0 0, minus 1. Okay? Now, question B. The graph below shows the point P and Q. P, Q, and R. This is Q here. This is R, and that's P. Now, the coordinates of Q, as you can see, is 0, 2. P is 4 and minus 1. R is 3 and 7. So, our first question. Write as a column vector in form X and Y, OP. OP is a position vector, so as long as you get the coordinate of P, we said in the previous video that we don't have to do any calculation, meaning ending point minus starting point. So this is just the vector 4 and minus 1. And that's all you have to. Simple, simple, simple. Come over here. The vector Q and R. So Q to R. Q is 0. Q is 0 and 2. R is 3 and 7. So QR, vector QR, is equal to ending point minus starting point. We don't have to do all the fancy vector triangle law there. And the ending point is 3 and 7 minus 0 and 2, which is 3 and 5. So this is the vector QR, 3 and 5. Good. Determine the magnitude of QR. We said the magnitude of a vector is written like this. I would like you to pause from everything we did in the previous video. As we're going through these questions, I would like you to pause and solve the question before you see the answer that I'm putting here. So square y square equal to, this is 3 and 5, so this is 3 squared plus 5 squared, 9, root of 9 plus 25, and this will give you what, 34? 34? Yeah, 34. And the root of 34, I don't have a calculator here, but it should be 5 point something. You write that in. Okay, so on the graph provided on page 33, draw the vector OS. OS is from the origin to 7 and 4. Show that PQRS is a parallelogram. So S is 7 and 4. Coming back over here, OS is, we have to draw the vector from O, the origin, to S, which is 7 here, and 4 there. So this is OS. This is S. OS is this vector here. Okay? Then we have to show that this here is a parallelogram. Well, sorry about that. You have to show that that's a parallelogram. So what do we know about parallelograms? Parallelograms, opposite sides are parallel and equal in length. So if we can prove that this side here is parallel to that side here and equal in length, then this one is parallel to that one and equal in length, then we can prove that this is a parallelogram. So you'll have to do it on the here, but I'm going to do the working on this side. We already know that QR is 3 and 5. So we just have to prove that PS is 3 and 5. PS, the vector PS, is equal to S minus P. 7 and 4 minus P is 4 and minus 1. 4 and minus 1. 7 minus 4 is 3. Yeah. 4 minus minus 1 is 5. So those two sides are parallel. They are equal vectors. So they are parallel and equal in length. So we have to find these two now. RS. Well, S minus, what was this? RS? This was PS, right? S minus R. So S is 7 and 4. R is, where's R? R is 3 and 7. 3 and 7. This is equal to 4 and minus 3. Then we have to prove that QS parallel to RS, QP parallel to RS is the same. So we have to find QP. So this is P minus Q. P is 4 and minus 1. Q is 0 and 2. 4 minus 0 is 4. Minus 1 minus 2 is minus 3. So, hence, if RS is equal to, is that QP, and QR is equal to PS, then it's a parallelogram. That's how you prove that. Okay. Is that the end of the question? That's the end of the question. So we can go on to the next question. Again, you can pause the video and try to solve these answers. So, in the point A, B, C, D, I have coordinates, all that you can see there. M is the midpoint of the line segment AB. Okay, good. Now, they didn't draw this diagram. I drew this diagram. And I would suggest to you that if you in the examination room and you encounter position vectors like these, or any vector, anything that they didn't draw a diagram, draw a diagram. When you draw the diagram, you get to see the answers clearly. For me, so they didn't draw a diagram, but I'm going to draw a diagram. A is at minus 2 and 8. Minus 2 here, 8 somewhere here, right? Sorry for this line here. Hope it doesn't be a bother. So this is the vector OA. Good. B is 4 and 2. 4 on the x-axis, 2 on the y-axis. This is B. How else could you have known how these things look if you didn't draw this diagram? So the first thing they ask for the answer is OB. We said for position vectors we don't calculate anything, we just put back the points. Then they want AB, from A to B. Or we can get that is ending point minus starting point, so that will be B minus A. B is 4 and 2. A is minus 2 and 8. So 4 minus minus 2 is 6. And 2 minus 8 is minus 6. So that's the vector BE. So they said M is on the midpoint of the vector AB. So if you draw the vector AB, M has to be the midpoint of this vector. So they ask for OM. So how do we get the vector OM? Okay, so there are two ways in getting that. Alright, if M is at the midpoint of AB, then we divide the vector by 2, which is 6 and minus 6. Is that one way of getting that? No, this is incorrect. Oh, what am I saying? We need to get... Okay, let me do it the traditional way. Let me do it the easy way, and then I'll try to remember how the other way is done. The easy way, if to find M, we need to find the midpoint of these two lines. x1 plus x2, y1 plus y2. So we find the midpoint of AB. So A is x1, y1, x2, y2. X1 is minus 2 plus 4, minus 2 plus 4 divided by 2. Y is 8 plus 2, 8 plus 2 divided by 2. This is 2 divided by 2 and 10 divided by 2. This is 1 and 5. So this is the midpoint here, 1 and 5. So the vector OM 1 and 5 is 1 and 5. So there's another way of doing it where you use the vector triangle law. OM, well, we would have had to find this point here. Okay. If I do remember how to solve this here using that vector way, I shall let you know. But this is incorrect. You don't divide the vector by 2. You have to find the midpoint. This is the correct way to do it. Find the midpoint of the line first, and then, but there are other ways of doing it. Okay, so we found all of these things. On the next side, we have to, using the vector method, show that AC and BD are parallel, and OB, sorry. AC, where is C? C is at 0 on the x-axis and 9 on the y-axis. So that's here. C 0 and 9. That's AC. And we have to show that AC and OB, A to C, this vector and this vector are parallel. So when vectors are parallel, they don't have the same magnitude, but they are going in the same direction. So how do we prove that? Well, when vectors are parallel, one will be the fraction of the other. So let's find, I'm going to solve it over here. AC is equal to C minus A, which is 0 and 9, 0 and 9, minus 0 and 9 minus A is minus 2 and 8. So that will be positive 2 and 1. That's the vector AC. We already know that OB is 4 and 2. What do you see? Are these vector parallel? Well, let's see. If we take 2 out of this bracket here, we have 2 there. And we have 2 times 2 is 4. 2 times 1 is 2. But this is 2 and 1. Isn't that the vector AC? So OB is actually 2 times AC. OB is actually 2 times AC. So hence, these vectors are parallel. Okay. We solved that already. The matrix M is defined as M da 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 da. Determine the value of P for which a matrix is singular matrix, and I did not mention this in the video on matrices, my apologies. Single matrix determinants are equal to 0. So when you're finding the determinant of a matrix, let's say the matrix A is equal to A, B, C, D, and you have to find the determinant of A, which is AD minus BC. If this determinant is equal to 0, if the determinant of A is equal to 0, then A is a singular matrix. Alright, let me give you an example. So if we had a matrix B equal to 6, 3, 4, and 2, is this a single matrix? Let's find the determinant. The determinant of B is AD minus BC, which is 6 times 2 minus 4 times 3, which is 12 minus 12, which is 0. So this matrix B is a singular matrix because its determinant is equal to 0. So let's get back to this here. If M is equal to 0, the determinant of M is the products of the elements in the leading diagonal minus the products of the element in the non-leading diagonal. So this is 2p times 1 minus 4 times minus 3, and that is equal to 0. If M is a single matrix, the determinant is equal to 0. So this is 2p plus 12 equal to 0. 2p is equal to minus 12. P is equal to minus 12 divided by 2. P is equal to minus 6. Okay, so A and B are 2 by 2 matrices such that A is equal to that and B is equal to that. Calculate 2AB. So this is 2 times A is 1, 2 minus 4 and 3, plus B is 5 minus 1, 0 and 2, 3. 2 times everything in here, scalar multiplication. So this is 2, 4 minus 8 and 6, plus 5 minus 1, 0 and 3. When adding matrices, we add corresponding elements or corresponding positions. So 2 plus 5 is 7, minus 1 plus minus, 4 plus minus 1 is 3, 8 plus 0 is minus 8, and 3 plus that is 9. Simple, easy 2 marks. Now you have to determine the inverse of B. The inverse of a vector is 1 over its determinant times its adjoint, B adjoint. So the determinant of B is AD minus BC, 5 times 3 minus 0 times minus 1, which is 15 minus 0, which is just 15. And the adjoint of a matrix is the changing of the positions of the elements in a leading diagonal and the change of the signs of the elements in a non-leading diagonal. So this 3 goes there, this 5 comes here, this becomes a positive 1, and this becomes what, a minus 0. There's no such thing as a minus 0, so it stays as a 0. But if a number was there, it would have been a minus number. Because it was positive there, it has to be negative there. And finally, you have to solve this question using the matrix. There's no space. Yeah, I have some space behind here. So let me just write it back quickly and solve it. 5, what is that? Minus 1, 0, 3, x, y, and 9 and 3. So we label this A, B, x and equal to B, and we have to find x is equal to A inverse B, so we have to find the inverse of A. We can do that quickly. Alright, so we have to find the inverse. Let's do it separate over here. So the inverse is equal to 1 over its determinant. There's an example of this in the other book, so I'm just going to rush this. We already find the determinant is 15. We already found the adjoint too, so we don't have to do that there. The inverse of A, oh, this was B. And now C. This vector, this matrix here is what we're using there. So we can't label it AXB. This one is B. And this one, let me just take that out. Good. So this one was the vector B all along. So this here will be X. And this one will be A. So X is equal to B inverse A. And we already found the inverse for this here already. So X is X and Y is equal to, I now remember that we didn't finish this off. This inverse, B inverse is 1 over 15 times this adjoint here, 3105. And this is what we have to use on this side. 1 over 15 times 3105 times this 9 and 3 on that side. So we have to multiply these two matrix, 1 over 15 outside there. Persons like to bring this inside. I don't, because it's easier to divide at the end. So this is 3 times 9. 3 times 9 plus 1 times 3. And 0 times 9. 0 times 9 plus 5 times 3. So 1 over 15. 3 9s 27 plus 1 3s is 3. 0 9. 0 times 9 is 0 plus 3 5 5 3s are 15. 1 over 15. This is 30. And this is 15. And 15 divides inside now. You have 30 divided by 15 and 15 divided by the 15. X and Y is equal to 2 and 1. And that's your vector video.